In this video, I'm going to demonstrate how to do the lateral analysis on a one-story, very simple building. Most of your buildings will not be this simple. However, this will show you just exactly how simple and easy Shearwall Pro is to use and how quickly you can get the lateral calculations done. And this will give you the engineering stamped. By the time you're done, you will have stamped engineering plans. So here's our example building. It's a very simple shop, and as we can see, there's, except for the front wall, there's really quite a lot of shear walls. This front wall right here, where there's two roll-up doors and three shear wall segments, that's really our biggest challenge for this project. I've put some dimensions on here, so as we can see, the building is 30 feet deep by 40 feet wide, and the wall height is 12 feet, and then from the top of the wall to the peak of the roof, we're just going to call that 5.5 feet, just to make this project easy. So let's get into Shearwall Pro. Let's start with our project name, and this is important that you put a good project name in here because this ends up going on in the footer of every single calculation sheet. Let's just call this the Awesome Shop. Our client is the amazing client. And our site location is, let's just say 123 any road. Then from here, we come down and we start selecting uh, some of the design criteria, which will be used to generate the wind and seismic lateral loads. You need the zip code because that will help to determine the seismic loads. The wind exposure, almost all of your buildings will be exposure B. The basic wind speed is preset to 98 miles per hour because that's what the city of Portland uses. 98 miles per hour ultimate wind speed. Shearwall Pro calculates the allowable wind speed. And then there's some dead loads and live loads for the floors and dead load and roof load and snow load for the roof. Weight of the walls, soil bearing capacity, and then your site class definition. This also ties in with the seismic. Um, that helps to generate what some of the peak ground acceleration forces are. And then here's just a table showing you what the assumed weights are. So let's get into it. All the Shearwall Pro calculates everything based off of grid lines. So you need to know what your grid lines are, and you need to know the distances between the grid lines in order for Shearwall Pro to calculate what the loads are to the walls. So in this building, you can see we have grid line A and grid line B at the top and the bottom of the page. And then at the left side of the page, we have grid line 1, which is the rear wall. And then we have grid line 2, which is the front wall. So I'm going to just type in grids A, B. I'm going to leave a space just to make things a little easier to see the differences. And then we're going to say grid 1, grid 2. Now we have to determine the direction. And you can pick whichever directions you want. You just need to be consistent. So let's take a look at the 3D and now the 3D model again. So the longitudinal direction is generally assumed to be the long direction of the building, which is almost always the direction of the main ridge. So, and the longitudinal direction is as if you are looking at the building along the longitudinal axis. So in this case, we're looking along the longitudinal axis, and this is the rear wall, as we can see, and then this is the front wall. So this is grid 1, and this is grid 2. And then uh, so our grids 1 and 2 are the longitudinal axis, So we're going to select longitudinal for 1 and 2. And that means grids A and B and the other direction are the transverse. Now we have to determine the distance from the datum. So let's go back to where our dimensions are, the shear plan. So let's assume that we have to pick a 0, 0 to be somewhere, and it can be anywhere. And your sign convention for distances can be anything you want. You just have to be consistent. So let's pick this point right here at the intersection of A and 1 to be our 0, 0. So, and we will measure horizontally, we'll measure positive distances to the right, and then we will measure positive distances down the page for in between grids A and B. So because grid, and so because we've determined this point right here to be our 0, 0, that means that grid A is the datum and grid 1 is the datum for, so grid A is the datum for the transverse direction and grid 1 is the datum for the longitudinal direction. So let's just go here and we're going to say grid A is at 0 feet from the datum because it is the datum. And then we know that, and then we have this dimension here that tells us grid B is 40 feet away. So we'll type in 40 feet. Now we'll come here, and we're again, grid 1 is at the datum, so it's 0 feet from the datum. And then grid 2 is 30 feet away from the datum. So we've done that part. And in this case, roof comes predefined as the top diaphragm because it doesn't really matter what your roof looks like. It's always going to be a roof. So the roof eave height from the ground. So if we go here to our north elevation, I've already put this dimension here as 12 feet. And then remember the distance from the top of the wall to the peak of the roof is 5.5 feet. So we're going to say this diaphragm height is at 12 feet. And then our ridge height is 5.5 feet. And then that determines our mean roof height, which is used in the wind calculations. Now we know and then here we are going to determine or enter our longitudinal transverse dimensions and the roof pitch, the roof rise. So we know our longitudinal dimension is 40 feet. Our transverse dimension is 30 feet. And our main roof rise is over here at the south elevation. It is a 412 roof pitch. 4 and 12. Okay, so we've got that part all done. So now we come down here to our roof gable data. So this is where we describe the shape of the roof, and that it helps to determine what the wind loads are. So just as a quick note, wall loads right here in this gable produce a higher wind pressure, higher wind force than the sloping roof right here. So when the wind blows on the sloping roof surface here, this is a lower pressure, lower force than when it blows right here. So it's important to know the difference. So we'll come over here. So we're looking at our longitudinal, we're looking down the longitudinal axis right here. And there's three groups, there's three areas, left of middle, middle, and right of middle. And what these three areas are is, so think of three triangles. So we have one triangle here that the bottom of the triangle is at the eave line, and then the gable wall, that is the middle triangle. Now, if there were dormers, there would be a triangle right here on the left side, and then you might also have another triangle here on the right side. So because we don't have dormers, we're going to say left of middle is no surface. The middle, which is right here, is a wall surface because it is a gable wall. And then the right of middle is no surface. There is no wall surface right here because there are no dormers. And then we come down here to the transverse roof. So now we're looking at it in this direction right here. And it's all roof. And so how you can estimate where the triangles are is draw a triangle, an imaginary line from eave to the center back to the eave. So now we have the center triangle, the left triangle, and the right triangle. And all three of those triangles are roof surfaces. So now we're set. We come down here and we review. In a one-story building, the diaphragm dimensions are always the same as they're always the same. Sometimes in multiple story buildings, the diaphragm dimensions can be different. So you can change those dimensions right here. And then so that is where these dimensions are. But then the number of walls this isn't just the number of shear walls. This is the total number of walls included, even interior walls in the building. And you don't have to get this exactly right, but you want to get a really good estimate for the number of interior walls. So right now, in both directions, we have a wall here and a wall here, and then we just have the exterior walls. So in both directions, we only have two walls. However, let's just pretend we had an interior wall right here. Then oops, didn't mean to do that. So let's just say we had an interior wall right here. So then in the longitudinal, because it's for loads this direction that the building has to support. Then if we had that wall in the longitudinal direction, we would say we have three walls. In this case, we only have two. So the default is two walls in each direction. And our walls weigh 8 pounds per square foot. So now we're kind of set to keep going here. I'm going to make this a little bit bigger, cut a little bit of it off. There we go. So here, the beginning of our solution grids are filled in. It says that grids A and B are in our transverse direction and they are 40 feet apart. Grids 1 and 2 are in our longitudinal direction and they are 30 feet apart. So here's how we start to assign loads to each of the shear walls. So at grid A, right here, it doesn't really matter which direction you look at it. Let's just say we're standing at this side of the building, at the rear of the building, and we're looking towards the building in that direction. So grid A is on our left and grid B is on our right. You can reverse these, it doesn't really matter. I'm going to do it this way just because this is the convention I've chose. So there are no shear walls to the left, and you can see things are already starting to get filled out down here. And don't worry about, if you haven't filled out all of the data, don't worry about these errors. They will correct themselves as you fill out the rest of your information about your building here. So there are no shear walls to the left. Grid B is the next shear wall to the right that will be receiving loads. Okay, now we'll do the same thing. Grid B, if we're looking at it in this direction, then grid A is the shear wall to the left, and there are no shear walls to the right. And then we can do the same thing here. None, 2, 1, and none. So now we have all of our loads, right? We know what the between wind and seismic, we know what the maximum loads are right here. And we can verify that between A and B, there's 40 feet, and between 1 and 2, there are 30 feet. And we know that to be true because this is what our building looks like right here. Now, let's come back up over here. We verify that our wall height is 8 feet, or 8 pounds per square foot, and our roof weighs 15. The dead load of our roof is 15 pounds per square foot. And you can change, if you want to change either of those, you come up all the way up to here, and this is where you can change them, or you can change them per diaphragm right here for each diaphragm. So we're going to come here and we're going to say our wall height. Remember, our wall height is 12 feet. And then, because this is a one-story building, we're going to pick hold downs because these are hold downs that will be embedded into the concrete. If this was a multiple story building and this was the second floor, we would pick straps, and then it would it would select the straps for us. I'll show you that difference here in a minute, what it does. It'll change what happens down here in the solution table. So now we need to know the sum of the length of the shear walls for each grid line, and we need to know the shortest shear wall. So the sum of the length of the shear walls tells us our unit shear force, and the shortest shear wall is used to calculate the uplift force. And also the tributary width of the roof or floor above. So what that is if we're going to look here at, so remember, this wall right here is grid, well, let's double check. That wall is grid B that we're looking at. This wall is grid B right here. And the trusses they span from grids 1 and 2. So grids A and B they're not load bearing walls. So we're going to say 0 and 0. And what these numbers are used for is it helps resist some of the uplift force if you've got some load sitting on top of the wall. And then for grids, I'm getting confused. Okay, that's right. Grids 1, this is grid 1, and this is grid 2. So we know that this length here is 30 feet. The tributary width, which is half of the span, is 15 feet. We're going to ignore the 2-foot overhangs for this example. It makes a small difference, not a huge difference. So now we are set to start typing in our shear wall lengths. So let's start with grid A. Grid A, we've already determined here that, so as you can see, we've already actually come up with a solution. We're going to verify that solution by doing this again. So we've already determined that we have designated this wall as a 13-foot long shear wall. And we can verify that it's 13 feet long by just putting a dimension right here. Boom, boom. Look at that, 13 feet. I'm going to Control Z and undo that. So the sum of the length of the shear walls is 13 feet because we only have one. And then the shortest shear wall is 13 feet because that is the only wall. So that is grid A. Grid B, we have the same thing, one 13-foot shear wall. Now let's come down here to grids 1 and 2. Grid 1, we have these 3 wall segments here. I'm going to put some dimensions on here just so that way everyone can see what we've got going on. We have a 10-foot wall. We have a 12-foot long shear wall. And we have another 10-foot long shear wall. Okay, so for this design example, we've already designated one 10-foot long shear wall. And we have one shear wall along grid line. Let's just verify. This is grid line 1 right here. We have one 10-foot shear wall. So we are going to say we have a 10-foot shear wall, and it's the only shear wall. So it is not only is it the sum, it is also the shortest. So now, grid line 2, we have more than one shear wall. Here we've designated 2 4-foot shear walls. So let's put some dimensions on here just to verify. That is 4 feet. Look at that. It's 3'6", and then we have another 4-foot long section of wall. So what we have done is we have said, now because there are more than one wall, we can let Excel do the math. I'm going to type in equals, which means this is a formula. I have a 4-foot wall plus another 4-foot wall. That adds them to 8. Now, the shortest shear wall is 4 feet. And look at that. It calculates. So we actually, so this is a project that has already gone to the building department. We put in hold downs a little bit bigger than what we needed to. So let's ask so here's one of the beauties of shear wall. Here's one of the best parts of shear wall pro. Let's ask ourselves some questions about this now. So I'm going to just kind of get everything set to where it's side by side. Let's look at grid line one. We've only designated one of these shear walls as uh, one of these wall segments as a shear wall, but we know we have three. Here's the question: can we get away without any hold downs if we designate all three? I don't know. Let's check that. Let's ask ourselves that question. So the sum of the length of the shear walls equals, because it's a formula, 10 feet plus 12 feet plus 10 feet. Our shortest shear wall is still 10 feet right here. And look at that. It says no hold downs. If we would have designated all three of these shear walls, we would have a wall. There wouldn't be any hold downs required. We didn't do that, so I'm going to Control Z and get back out of that. Now let's ask ourselves another question. Same question. If we designate all three along grid line two, if we designate all three of these as shear walls, can we get away with no hold downs? We already have our formula here, so all we have to do is add the 3.5 foot shear wall. And without even changing this, let's just change this here. Grid line two, nothing changed. So if we wanted to designate this in the middle here as a shear wall, we would be adding hold downs to the building unnecessarily, and it would not change the performance of the building. So I'm going to Control Z, got back out of that. So then let's ask ourselves another question. What would happen if we only need one of these 4-foot wall segments? What does that look like for hold downs? Look at that. So it increases our nailing to a type C shear wall, which is 8 penny at 3. But the bigger issue is that these type 10 hold downs, HDU 11s, they require a much larger footing to be installed at each of the points where you have the anchor bolts. So I'm going to make the judgment call and say it's probably easier to install smaller hold downs, more hold downs that are smaller, than it is to install the larger footings. And it probably costs less money too, because you don't have to form the larger footings, you don't have to buy more rebar. There's a lot of things you don't have to do if you just put in two more hold downs. So I'm going to Control Z, make that 8 feet, and look at that. We're done with the calculations. So this is what you would then save and send to us, and we would then unlock the spreadsheet, print out the calculations after we review it, and send back to you. Then what you do is you create the drawings. And in this case, the drawing looked like this. So the designer sent us this Revit model without the stamp on it. After I reviewed it, I put the stamp in, and then the designer has access to the shear wall schedule, the hold down schedule, and all of these shear wall and footing details that are necessary for a complete lateral design. So as you can see, this is very useful, very handy, and very quick. If you have any questions, get a hold of us. I hope to see you on your next Shearwall Pro project.